Hello class, so this is going to be my first lecture as a proper video lecture. So till now we were doing audio lecture plus handwritten notes in tandem. So today we will be discussing the stability requirements of retaining wall. Now this particular lecture I had already supplied you as audio lecture, but since this is the first time I am starting out with video lecture, I would like to start with something you already know. Okay, so those who have followed the earlier lecture, hopefully this will be a revision. So those who have any doubts, hopefully this lecture will clarify that for you. Okay, so stability requirements of retaining wall. Now we had told this over and over again. When it comes to retaining wall design, the stability check is almost as equal or as equally important, or probably more important than the actual strength checks, because there is the risk of retaining wall sliding or overturning as a whole. So there is no point in designing the members to resist the load unless the retaining wall as a whole is stable. Now with regards to stability, we had said there are two things: there is overturning and there is sliding. So the requirements for stability check, and not just for retaining wall, for any general structure, is given in clause number 20 of IS 456. So let's go there. So you have, this is clause 20, stability of structure. So you have 20.1 for overturning and 20.2 which is for sliding. So this here basically it's giving you a factor of safety. So for stability checks for both overturning as well as sliding, there is a special factor of safety that is specified by the code. It's 1.4. Okay, so the net factor of safety for overturning and sliding should be 1.4, and for the carrying out the stability check, you have to take only 0.9 times the stabilizing force or moment. Now in most cases, stabilizing force or moment constitute nothing but the self weight of the structure, right? So it's the self weight of the structure which is trying to stabilize it against the destabilizing external force. So when you are doing this stability check, you have to consider a factor of 0.9 times stabilizing force. Now this is similar to what we saw in table 18 of the IS 456 for load combination. So let's go there if possible. So this is table 16. Yeah, so this particular table we had seen it when I circulated the Excel sheet on different load combinations. So here we saw seen that one of the load combinations involving dead load plus wind load or earthquake load is with 0.9 times factor for dead load. So that is basically the load combination which is for stability check. So in stability check, lesser the gravity load or dead load, the more vulnerable the structure is to be unstable. That's why we are taking 0.9 times dead load. So here also the philosophy is something similar. So let me go back to the clause page number 20. This is 22. Yes. So here that's what we will do. So you will take 0.9 times the stabilizing force or moment by destabilizing force, and the factor of safety, it should be at least greater than 1.4. So if it's not satisfied, you have to redesign the sectional properties. So here I mentioned stabilizing force or moment, destabilizing force or moment, because you have two things, because in the case of overturning, it's the moment that's trying to destabilize. Okay, so in that case we'll take the moment, and in the case of sliding, it is the force So anyway, we'll come to that in a short while. So let's first discuss overturning. So you try to imagine this: you have a retaining wall. On one side you have soil with a higher level, and another side you have soil at the ground level. So what's really trying to overturn this retaining wall is nothing but the soil which is here, right? So that soil with its active earth pressure, it's trying to overturn the retaining wall. So basically it will be trying to overturn the retaining wall about its toe. So remember, we discussed there is toe as well as there is heel. So it will try to overturn the retaining wall with respect to the toe, and that's the point about which we have to check the overturning stability. So there are two things: there is MO, which is nothing but the overturning moment, the moment which is trying to overturn, and then there is restoring moment, the moment which is trying to stabilize the retaining wall. So let us look at what will be MO and MOR for the two different cases that we have seen so far. So in the case when you have a sloping backfill, as we said, this is the pressure diagram. It will be at a slope. So PA is the active earth pressure. It will be inclined parallel to the slope angle theta, and it will have a vertical and horizontal component. And then there is W, which is the resultant of all the weights. Okay, it also includes the weight of soil which is resting on the heel portion of the slab, because that is also stabilizing the structure. So MO, or overturning moment, is nothing but horizontal component of active earth pressure PA cos theta into h dash by 3. So h dash is the total height here. H dash by 3 is this height, which is the centroid of the triangle. So using that you will get the overturning moment. So that is the overturning moment. Now PA, you have already seen this. It is the area of that total triangle and the length of the retaining wall. Anyway, we are taking it as unity. So you will have a h dash square here. So you have an h dash here. So cumulatively they will become h cube. And since you have a half in PA, you have a 1/3 here. There will be 1/6. So this is the resultant expression that you get. Now restoring moment. When it comes to restoring moment, as we said, primarily you have this W, the self-weight of all the things, which is acting at a certain point. The resultant of that is acting at a certain point, let's say at a distance of xw from the heel portion. Okay, so when you are taking the restoring moment, which is nothing but the moment that, about toe portion, it is this is the force W, total W into lever arm. So what will be lever arm? This base slab width is L, this much is xw. So the lever arm is nothing but L minus xw. So that is this portion, W into L minus xw. Now in the case of sloping backfill, you also have the vertical component of active earth pressure. So if you look at it, that's also actually contributing in the restoring moment. So you will have PA sin theta into L. So PA sin theta is a vertical component into L is the lever arm. So that is about sloping backfill. Now when you come with level backfill with surcharge, assuming the general case, so overturning moment, it consists of two parts. So as we discussed, when you have the level backfill with surcharge, you have a rectangular active earth pressure diagram and a triangular portion. So the rectangular portion will be having the resultant as PA1 acting at h by 2, and then you have PA2 for the triangular portion acting at h by 3. So the total overturning moment about the toe is PA1 into h by 2 plus PA2 into h by 3. So that's simple. And restoring moment is nothing but the contribution of W. There won't be the vertical component of active earth pressure as we saw in this case. So it is simply W into L minus XW. Now with the MO and MR, or overturning moment and restoring moments calculated, we'll calculate the factor of safety, and hopefully it will be lesser than 1 point, it will be greater than 1.4. If it is less, we have to revise the design. Okay, so that's about overturning moment. Now let's come to sliding check. So in the case of sliding, what happens is, as we know, this retaining wall as a whole, it will try to move towards left. So on the right side you have that earth backfill, right? So you'll try to move towards the left, and as a result of it, there is a chance of it sliding. So basically, when it tries to slide, what is resisting it against sliding is nothing but the frictional resistance that is developed. So if you consider mr, capital R, as the resultant of all the vertical forces acting between retaining wall and ground, the R will act, and as a result of that R, due to the friction between retaining wall and ground surface or the soil, you will have a force which is mu into R. Here mu into R is nothing but coefficient of friction between soil and the retaining wall into total R. That's the basic principle of mechanics. When you try to slide anything, what is opposing the motion is the force developed between contact surfaces, which is nothing but coefficient of friction into the reaction. So now this coefficient of friction varies with the type of soil. Of course, retaining wall is RCC only. So if it is a silty soil, the coefficient of friction between soil and retaining wall is 0.35. That's on one extreme. If it is rough rock, then the coefficient of friction is 0.6. So basically it varies from 0.35 to 0.6. So when you, due to this active earth pressure, when it tries to slide the retaining wall, what's trying to resist it is nothing but the frictional force that's developed. So again, we treat separately the case with sloping backfill and the case with surcharge. So these are the diagrams. Now I have not drawn the soil depth on the other side, but anyway, it is there. So the case of the one with sloping backfill, just like we said in the last time, you have a horizontal component PA cos theta and a vertical component PA sin theta. So what will try to slide is the total horizontal component, which is nothing but PA cos theta. Okay, and what will try to resist is the frictional force that's developed. So again, you use the factor of 0.9 as we have seen in that codal provision. So see, this is the 0.9 for sliding, and times F. So what is F? Mu into R. So here in the case of sloping backfill, R consists of two parts. One is the total W, of course, and then the vertical component of active earth pressure. Now the case with surcharge, here what happens is you have two active earth pressures components that you need to be to consider. One is that due to surcharge PA1, and then due to the actual active earth pressure PA2. So PA1 and PA2, but in this case F will have only component due to W. So these are the stability checks you will perform for the two different cases. Now what happens typically is, when you have surcharge load, it's observed that it is difficult to satisfy the stability check at the first instance. So especially when you have a heavy surcharge. So what happens is, of course, one solution is you can revise the section and things like that, but revising the section will be an uneconomical option, plus there will be other complications related to it. But a simpler option that has been devised uh, for retaining walls to satisfy this sliding check is providing something known as a shear key. So shear key is provided at the underside of the base slab. So we will see in this blown up image. So I'm not drawing the full retaining wall. It's only a part of the retaining wall. So you have basically a shear key here. So it's like a rectangular section which is passing throughout the length of the retaining wall. So the position of the retaining of the shear key should be such that the reinforcement, the tension side reinforcement from the retaining wall bar can be extended like this. So that's the position, because we said that for a retaining wall, as we discussed in the first lecture, this is the tension side. If you have soil here, this is the tension side. So main tension reinforcement is here. So that reinforcement you should be able to extend it like this. That is the geometrical placement of shear key, sorry. And DSK is the depth of the shear key. XSK is the distance of the shear key from the toe portion. Now what happens is, see, when you try to construct it, you will be excavating soil from this soil is excavate, this soil will excavate. So then you will put the reinforced shear key, concrete and things like that. So basically this portion of the soil is undisturbed. So as a result of that, there is passive earth pressure that is mobilized. So the retaining wall is trying to push along this direction. So this passive earth pressure is trying to resist it, which means it will contribute in resisting the sliding. Now passive earth pressure distribution we have seen the diagram. So it's a triangular distribution. Now first and foremost, researchers have shown that 300 mm of initial overburden, it is not significant. So it will be loose topsoil, so we can neglect that. Plus the portion of passive pressure up till toe portion, we have anyway neglected it, as I discussed in the last lecture. So basically what we'll be having is, you will have this trapezium shape, right, which is part of the original triangle like this. So you have H, this is the H1, this total is H2. So here this is the total resultant of the passive earth pressure. Now passive earth pressure we have seen in which, so in passive earth pressure you have passive earth pressure coefficient, which is the reciprocal of active earth pressure coefficient. Now it's also been proven that the net passive earth pressure is not just up to this level. So you will have a angle phi. Phi is the angle of repose, of course. So this much depth, which it will be effective in the passive earth pressure. So this is the additional passive earth pressure resistance that you get due to the shear key. Okay, so remember, why did we provide shear key? So shear key is basically to increase the sliding resistance, since it is failing in the sliding check. So you provide the shear key. So based on this shear key, you will get this passive earth pressure diagram. So the resultant of this will be the extra passive earth pressure, which will minimize the sliding or increase the factor of safety in sliding. So you again rework the calculation using the passive earth pressure. Of course, this is based on simple geometry that you discussed. The resultant of this, which is the area of total triangle minus area of this smaller triangle. So now using this passive earth pressure contribution, you rework the factor of safety in sliding, and hopefully it should satisfy. So if it's not satisfying, you play around with this dimension. So that is about sliding check, including the concept of shear key if it is not satisfying. Then finally, this retaining wall should satisfy soil bearing pressure requirements. So it should resist excessive settlement, and it should not have tilting and rotation, and of course the concept of SBC and things like that, which we had discussed in the first unit of this syllabus. Okay, thank you.